In our last video, what we understood is how do we deal with the soils which are just sandy, right? So, in the last video, what did we derive? We got an expression for, what is this? Alpha F, okay? What is alpha F? 45 plus beta by 2. What is beta? Obliquity, okay? And at failure, obliquity beta m is always equal to phi. So, when we are dealing with sandy soils, we can always, first of all, the failure criteria is maximum obliquity, and a soil will fail when the obliquity reaches maximum internal friction angle. So, moment the slope or this particular angle, beta, okay, I don't know whether the cursor is visible, reaches phi value, there will be a sliding failure of the soil. So the equations that we studied, first of all, was alpha F is equal to 45 plus beta by 2. For numericals, when you all have a statement saying that soil is at failure and impending failure, this beta can be taken as a value equal to phi. Second relationship, we got sigma 1 by sigma 3 is equal to 1 plus sine beta m upon 1 minus sine beta m. Again, this beta can be replaced by phi when the soil is at failure. Okay, so both these equations are for C is equal to 0. What type of soils? Frictional soils, non-cohesive soils. Then we have a general equation for sigma, normal stress, in terms of principal stresses. Okay, so this is what we learned in the last video. Alright, now how do we deal with C5 soils? First and foremost, this equation alpha F is equal to 45 plus beta by 2, which is equal to 45 plus phi by 2, remains same. A typical Mohr circle diagram for C5 soils will look like this. Have a look at this figure. What all things have I marked on this? This particular origin is O. Now, what will be this arrow depicting? This arrow, the grey arrow, okay, this is going to depict C. What is C? Origin, small c, okay. Then the slope of this line is telling you frictional angle, that is phi. Please see, where have we marked alpha F? So this line MA is representing failure plane. The angle that failure plane makes with the horizontal is alpha F, okay, alpha at failure, okay. Now this line, red color line, is going to be perpendicular to this gray line. Why? Because this gray line is depicting radius, okay, and tangents are always going to be perpendicular to radius. So in that case, this is 90 degrees. This is 90 degrees. This is alpha F, okay, and this value inside is going to be 90 minus phi. Is that understood? And the external angle here is going to be 2 times alpha. This is by pure geometry. Okay. Now, what is the radius? Radius is always given by sigma 1 minus sigma 3 divided by 2. And the distance of the center, if I mark this point, okay, if I mark the center of this point as, let's say, C, this is small c, okay, and this is capital C. How do I, let's do it like this. Okay, this is small c, this is capital C. Okay. The distance of this C from the origin is given by alpha 1 plus alpha 3 by 2. This is for all the types of soil. Okay, this is nothing new. The radius is alpha 1 minus sigma 1 minus sigma 3 by 2 is nothing new. This is common for all the Mohr circles here, respective of the type of soil. Right? So from this particular figure, you can derive the other relationships. Okay, so now the equation that we have in terms at failure for alpha F, okay, for alpha F, that means failure in C5 type of soil, we can write sigma 1 as equal to sigma 3 tan squared alpha F plus 2c tan of alpha F. How do we write an equation at failure for C is equal to 0 type of soils? So for C is equal to 0 type of soil, at failure, when will the failure occur? I have already told you failure will occur when beta is maximum. At beta m, we have equation at sigma 1 by sigma 3 is equal to 1 plus sine of beta n upon 1 minus sine of beta n. Again, beta n is related to alpha f. So the same parameters that we just now saw, we wrote an equation for C5 soils in terms of sigma 3, okay, and C, because C is present here, that C will not be present. And for C is equal to 0 type of soil, it was in terms of beta, which could further be related to alpha F. So this equation can be a counterpart, C5 counterpart of this particular equation. Which one? This. Okay, and this is a general equation. This is not at alpha F. This is at any state but not at field. This is a general equation for C5 type of soils. So don't get confused. You should know when which equation has to be used based on the problem statement. Right? So now let's go ahead. Now this same equation can be rewritten, okay, as sigma 3. Okay. So basically what I have done, actually this is a step you will get while you derive this equation. Okay. So if you go to the derivation part of this particular equation, this is preliminary stage before you get this. Why I have written this, I will tell you later. Okay, now what you have is sigma 3 can be written as sigma 1 minus sine of alpha upon 1 plus sine of alpha minus 2c under root of 1 minus sine of phi upon 1 plus sine of phi. Now same thing, ulta, you take it on the other side. In place of sigma 3 I am writing sigma 1. In place of sigma 1 I am writing sigma 3, and this 1 plus upon 1 minus gets interchanged. This minus becomes plus, and again plus upper minus term. Okay. Now this term 1 plus sine phi upon 1 minus sine phi. Okay. In your 4th unit, I do not know whether you all have covered this, but there is something called coefficient of active earth pressure, coefficient of passive earth pressure. Probably you all might have used these coefficients when you all have designed retaining walls. Okay. Now what is this coefficient of active earth pressure that Sarpa ma'am will teach you in the 4th unit? It's basically when you design a retaining wall, and a retaining wall moves towards the backfield. Okay, so you have a retaining wall and you have this backfield. If the tendency of this retaining wall is to go in this direction, okay, the wall is said to be under active earth pressure. Okay, when the wall is moving away from the backfill, it is considered to be under active earth pressure. If the wall is moving towards the backfill, okay, then it is under passive thrust. Okay, accordingly, there is something called coefficient of active earth pressure and coefficient K suffix A, and this is coefficient of passive earth pressure. Now this coefficients Ka is given as 1 minus sine phi. I have just given you a very brief description about what is earth pressure. There is a whole chapter on it. You will learn it in detail later. Okay, or you might have already learned it. I am not sure about that. And Kp is actually 1 by Ka. So ulta, 1 plus sine of phi upon 1 minus sine of phi. Okay. Now, if I substitute this in these two equations, sigma 3 and sigma 1, what would I get? Sigma 3, I am substituting value of Ka in this equation. Okay. So this sigma 3 can be written as sigma 1 into Ka minus 2c under root of Ka. Understood? Okay. So now we will solve a problem. Okay. So we have a statement for this problem. A cylindrical soil specimen having cohesion is equal to 80. What is the unit of cohesion? It's always same as the unit of stress. Where do we plot cohesion? On the axis which represents tau, shear stress. So your unit is always going to be same as stress. Please remember this, okay? So it has a cohesion of 80 kilonewton per meter square and the angle of friction is equal to 21 degrees. It's subjected to a cell pressure of 100 kilonewtons per meter square in a triaxial tester. Okay, compute. There are two things you are asked to determine. One is maximum deviator stress at which the sample will fail. What is deviator stress? When you have a triaxial testing machine sample, what happens? First you increase the sigma 3. See, I'm just assuming that you people have watched those videos on triaxial testing machine. Please watch those videos. Half the things get clear with the videos itself. So first you have a sample which is enclosed in a rubber membrane. Okay, and then around it there is a cell. Okay, and in this cell what happens? You inject fluid. So this fluid is all around. Okay, so sigma 3 is in this direction, and when you are injecting sigma 1 which is in this direction is always going to be same as sigma 3 because it's the fluid which is applying pressure in the downward direction. So initially sigma 1 and sigma 3 is same. Then what happens? Once this is done, then you add additional vertical pressure. Okay, so this additional vertical pressure causes the sample to fail. That additional vertical pressure is called sigma D. Okay, so now what will be sigma D? Okay, additional, not the total. So that sigma D that is additional is always given as sigma D is always given as sigma 1 minus sigma 3. All these things are done before. I am just revising. Okay, so maximum deviator stress at which the sample will fail is asked. Okay, and the angle made by failure plane with the axis of specimen. So first let's jot down what is given to us. So the data that is given to us is sigma 3 is equal to 100 kilonewtons, C is equal to 80 and phi is equal to 21. What is asked? Maximum deviator stress and alpha f, the angle made by the failure plane with the axis of specimen. If phi is given, how difficult it is to find alpha f? Correct? So my alpha f will be is equal to 45 plus 5 by 2. So that is, you add phi is equal to 21, you get the value as 55.5 degrees. Simple. Then the second thing that is asked is deviator stress. What is deviator stress given as? Sigma D is equal to sigma 1 minus sigma 3. How difficult it is to find sigma 1 and sigma 3? Right? So first thing is, let's find sigma 1. Which equation? So we have an equation for sigma 1 in terms of sigma 3, in terms of alpha and C. All these parameters are given to you. Substitute them. So you substitute the value of sigma 3 as 100, alpha f is 55.55, C is given to you as 80. Okay, you get the value of sigma 1 is equal to 443. Next up, let's determine what is sigma D. You know sigma 1. Okay, you know sigma 3 which was already given in the problem. You get the value as 343 kilonewton per meter squared. Okay, now what if, let's find something more because we don't have time to solve many problems. Let's say you were asked to find normal stress on the failure plane. How would you find it? So remember the general equation for C5 soils that we just studied, we revised it. So this is a general equation. Now we know the value of alpha f. So at alpha f, your sigma will be sigma f. So you again substitute everything in this particular equation. So substituting the value of sigma 1, sigma 3, alpha, you get sigma f is equal to 210. Now we have got the normal stress. Can we find the shear stress? Equation for tau is given as sigma 1 minus sigma 3 by 2 into sine of 2 alpha. Again, we are dealing alpha at failure, so your tau also will be at failure. So I write it as tau f is equal to, substituting the value of sigma 1, sigma 3, 443 minus 100, alpha is equal to alpha f, you get the value of 160 kilonewton per meter square. Now, all this what you did can also be done graphically. So in any particular problem, let's say you are asked to find all these values graphically. It's very simple. All you need to do is draw the Mohs circle. So let's understand how we draw the Mohs circle.